Our world, it just feels so random, right? I mean, from the stock market to the weather, chaos seems to be the name of the game. But what if I told you that hiding underneath all that randomness, there's a predictable, almost beautiful order? That's what we're going to dig into, how to find the signal inside all that noise. And it all kicks off with this question that honestly feels like it shouldn't work. We see it constantly, especially around elections, right? A pollster talks to maybe 1,000 people, a tiny, tiny fraction of a country, and then they get on TV and claim they know what millions of people are thinking. And the crazy part is, they're often pretty accurate. How on earth is that possible?
So, what's the secret? Well, it's not magic, it's math. There are two incredibly powerful ideas in statistics that work together to pull that order out of the chaos. And we're about to break them both down.
Okay, so our first big idea is something you probably already get on a gut level. It's called the law of large numbers, and it's all about one thing, inching closer and closer to the actual truth.
So here's how it works. Imagine you flip a coin. If you only flip it twice, you could easily get two heads. Your average would be 100% heads, which is, way off from the true 50-50 odds. But what if you flip it 1,000 times? Or 10,000? All those random flukes start to cancel each other out, and you can bet your bottom dollar that your average is going to be really, really close to 50%. The more data you add, the sharper the picture gets.
And check out how fast this thing works. It's kind of wild. After just 10 flips, your odds of being close to the true 50% are only about 65%. It's okay. But jump to 100 flips, suddenly you're 96.5% certain. That's a huge leap. By the time you get to 1,000 flips, it's basically a lock. The uncertainty just melts away.
Okay, so here's the bottom line. The law of large numbers gives us a destination. It tells us that our average is on a journey, and that journey always leads straight to the true underlying average. It's like a homing beacon for the truth.
But, okay, knowing where you're headed, that's only half the story, right? It tells us where we're going to end up, but it doesn't really tell us anything about the path we take to get there. And this is where things get really interesting.
Just think about it for a second. Let's say 100 different polling companies all go out and survey 1,000 people each. They're not all going to get the exact same number. One might get 51%, another might get 53%, maybe one gets 51.5%. So what's the deal with all those different results? Are they just random, all over the map?
So let's get this straight. The law of large numbers tells us where the average is going. It's heading straight for the true value. But this next question is all about how all those different attempts, all those different sample averages, are scattered around that true value. And the answer to that how, well, it's just mind-blowing. And that brings us to our second big idea, the central limit theorem. Seriously, this is one of the most amazing and just flat-out beautiful results in all of mathematics. It uncovers this hidden pattern that literally emerges from pure randomness. Okay, get ready for this, because this is where the magic happens. It doesn't matter what your original data looks like. It could be completely lopsided, totally chaotic, just weird. The central limit theorem says that if you start taking the averages of samples from that data and then plot those averages, they will always, always form a perfect symmetrical bell curve. It's like a universal law of data physics. Okay, just look at this. We're starting with some really messy, skewed data. It looks nothing like a bell curve. But now, let's start taking averages of little groups of samples. With just 4 at a time, you can see the shape is already starting to shift. At 16 samples, yeah, it's definitely getting more symmetrical. And by the time we're averaging 64 samples at a time, boom! A perfect, beautiful bell curve just appears almost out of thin air. And look, this bell curve showing up isn't just some cool math trick. It is incredibly useful because this shape, the normal distribution, it follows a very strict, very simple set of rules. And that gives us the power to predict things. So here's rule number 1. About 68% of all of our sample averages are going to land within one standard step away from the true center. You can think of that as just one standard-sized step away from the middle. Now, if you take 2 of those standard steps out from the center, you capture about 95% of all the possible results. And this number, 95%, that is the magic number. It's the gold standard for confidence in, well, pretty much everything from science to manufacturing. And if you go out 3 steps, you've got 99.7% of everything accounted for, which is, pretty much all of it. This amazing predictability is the key that unlocks this whole puzzle. Okay,
So now we've got our two heavy-hitting tools. Let's circle all the way back to that polling question and see how the central limit theorem makes it all work in the real world.
Right, that whole plus or minus 3% margin of error thing you always hear on the news, where in the world does that number come from? Well, it comes straight from the predictable shape of that bell curve we just uncovered.
Let's just walk through it. Say you poll 1,000 people, and 52% of them support a candidate. The central limit theorem tells us that there's a 95% chance that your result is within those two standard steps of the actual truth. It turns out there's a beautifully simple formula for this two-step window, which we call the margin of error. It's roughly 1 divided by the square root of your sample size. So, for 1,000 people, you do the math, and what do you get? About 0.0316, or around 3%.
And that is what it all means. When you hear a poll says 52% with a 3% margin of error, they're saying they are 95% confident that the real number for the entire country is somewhere between 49% and 55%. It's not a wild guess, it's a statement of probability, and it's all thanks to the central limit theorem.
So, what's the big takeaway here? We've learned that what seems like total randomness on the surface is actually humming along to these deep, hidden, and predictable patterns.
You've got these two amazing tools. Think of it like this. The law of large numbers is your camera's focus dial. The more data you collect, the sharper the picture of the truth becomes. And the central limit theorem, it tells you that no matter how blurry the world is, when you average things out, the picture always clears up into that same perfect bell shape.
And that is why this is so important. These mathematical laws are what allow us to make sense of an uncertain world. It's how insurance companies can predict risk, how factories can make sure their products work, and how scientists can test new medicines, all by finding that hidden order in a world that just seems full of chance.
It really makes you wonder, doesn't it? If we can find this much predictability in something as messy and chaotic as human opinion, what other hidden patterns are out there, just waiting for us to find them, if only we knew to look at the averages?